Welcome to Orbit Observer. It's lovely to have you here wherever you are. Whatever corner of the world you've curled up in tonight, whatever the hour is where you are right now, settle in. Pull the blanket a little higher. Let your shoulders come down from wherever they've been all day. You don't have to do anything for the next little while except breathe and listen and let your mind wander somewhere very far from here. Before we drift off together, let me say a quiet thank you. If you enjoy these slow journeys through the night sky and want more of them, a gentle like and subscribe really does help this sleepy little channel keep going. Small creators like me rely on that kind of small kindness more than you'd think. And to those of you who've already subscribed, who come back night after night to drift off up here in orbit with me, thank you. Truly, I'm glad you're here again. So while you're getting comfortable, I'll ask the question I always ask. Where in the world are you watching from tonight? What time is it in your corner of the dark? I love imagining all of you scattered across the planet, lamps still glowing, eyes getting heavy, all listening to the same soft voice describing the same strange and beautiful place. And tonight, the place is far, very far. Tonight, we're going almost 1.5 billion kilometers from your bed, out past the asteroids, out past Jupiter, all the way to Saturn, and then a little further still to one small moon, swaddled in orange haze. Its name is Titan, and I should warn you, the way I always do, that this one might be a little too interesting. I'll try my best not to keep you awake. But if I do, well, at least you'll have learned something wonderful about a world made of fuel and rain and frozen rock. A fair trade, I think. So if you drift off before the end, that's perfectly fine. Truly, the methane seas will still be there when you wake. Titan has been quietly doing its strange things for billions of years, and it will keep doing them whether you're conscious for the next sentence or not. There's no need to follow every detail, no need to hold every number in your head. Just let the ideas wash over you the way the haze washes over that little moon, soft and orange and endless. We'll move slowly, one mystery at a time. No rush, none at all. Let me paint you the picture first. Let me put you there on the surface of Titan, just for a moment before we talk about why it matters. Imagine you're standing on a shoreline. Not a beach exactly, but the edge of something. Behind you, low rolling hills of dark material, almost black, fine as soot. Above you, no blue sky at all. Instead, a thick orange dome, a kind of permanent golden dusk, as if the whole world were lit by candlelight filtered through amber glass. The sun is up there somewhere, but you'd never find it through all that haze. It's a dim, hazy day, and it's always a dim, hazy day, and the light is the color of weak tea held up to a lamp. And in front of you, lapping very gently at the shore, almost too gently, is a sea. A real sea. It stretches to the horizon, dark and still, so still it might be a sheet of polished stone. You could stand and watch it for an hour and see barely a ripple. And here is the first strange thing, the thing I want you to hold on to as we drift off tonight. That sea is not water. It cannot be water, because where you're standing it is about 179 degrees below zero, minus 179 Celsius. That's about 94 degrees on the Kelvin scale if you've ever met it, which is just the temperature scale scientists use that starts at the coldest anything can possibly be, 94 notches up from the absolute floor of cold. Cold enough that water, the stuff that fills your glass and your oceans and your own body, would never, ever be liquid there. On Titan, water is rock. It's frozen so hard it forms the bedrock, the actual stone of the place. The mountains are ice, the pebbles are ice, the ground beneath your boots is water-frozen rock solid, harder than granite. So what's the sea made of if not water? Methane and ethane. Now I know those sound like chemistry class words, so let me just hand you the plain version. Methane is the simplest thing that can catch fire, the same gas that hisses out of your kitchen stove before the flame takes hold. It's natural gas. On Earth, it's invisible, it's a vapor, it burns. But out there, where it's so unimaginably cold, methane gets squeezed and chilled until it gives up and becomes a liquid. The way steam becomes water when it cools, the way water becomes ice. It pools, it flows, it fills entire seas. So when I tell you Titan has a sea of liquid methane, what I'm really telling you is this: Titan has oceans of fuel, cold, clear, liquid fuel, sitting there in the open under an orange sky. If you could somehow carry a match there, and if there were any oxygen in the air to let it burn, which there isn't, you could set the whole sea alight. But there isn't, so it just sits there, perfectly calm, a lake of stove gas turned to liquid by the cold. And ethane is methane's slightly heavier cousin, same family, just a little bigger, a little oilier. The two of them mix together in those seas, methane and ethane, a kind of natural fuel cocktail, and that mix is what laps so gently at the shore where I've set you down. Now, let me tell you the thing that first made me want to talk about Titan tonight. The thing that I find genuinely hard to believe, even though it's true, it's about how clear that liquid is. We have a spacecraft to thank for knowing this, a spacecraft called Cassini. We'll talk much more about Cassini and its little partner Huygens in a moment, because they're the heroes of this whole story. But for now, just know that Cassini was a robotic explorer the size of a small bus, and it spent 13 years orbiting Saturn, swinging past Titan again and again and again, peering down through that orange haze. And it couldn't see through the haze with an ordinary camera. The smog is too thick. So instead it used radar. Radar is just a way of seeing with radio waves instead of light, bouncing a signal off something far away and listening for the echo, the way a bat finds a moth in the dark, the way a ship finds the seabed beneath it. You send out a pulse, you time how long the echo takes to come back, and from that you build a picture of what's down there. So Cassini aimed its radar at one of Titan's seas, a sea called Ligeia Mare, and it sent its pulse down through the haze, down to the surface, expecting the echo to bounce off the top of the liquid and come straight back. But that's not what happened. The radar went down, touched the surface of the sea, and then kept going. It passed straight through the liquid all the way down to the seafloor, 160 meters below, and bounced off the bottom and came back up. 160 meters, that's taller than the Statue of Liberty stacked on top of itself with room to spare, and Cassini saw the bottom of it, as if the entire sea were made of glass. Sit with that for a moment here in the warm dark. On Earth, you cannot do this. You point radar at the ocean and the echo comes off the surface, because our seawater is full of salt and silt and life and churning bubbles, a murky soup that radio waves can't penetrate. But Ligeia Mare is so pure, so unbelievably clean and clear that the radio waves slid right through it as if it weren't there at all. No silt, no salt, almost nothing dissolved in it, not even much of the nitrogen gas you might expect. Just a near-transparent body of liquid methane and ethane, 160 meters of crystal-clear fuel lying still and cold under the haze, with the spacecraft staring straight down to the rocky ice at the bottom. I find that almost unbearably beautiful, honestly. A sea you could see all the way through, a sea clearer than any water that has ever existed on Earth. And it's just sitting out there right now, this very night, exactly as still and clear as I'm describing it, while you lie there getting sleepy. It's there whether anyone's looking or not. So let me tell you about the two spacecraft that found all this, because they deserve the telling, and because their story is a soothing one in its way. A long, patient voyage and a single brave little fall through the haze. The mission was called Cassini-Huygens. 2 names because it was really 2 machines bolted together for the journey. Cassini was the big one, the orbiter, the bus-sized explorer that would circle Saturn for years. And tucked onto its side, like a passenger riding shotgun, was a small probe called Huygens. A squat little thing, shaped a bit like a wok or a clamshell, whose entire job was to detach, drop down through Titan's atmosphere, and land. To touch the surface, to become the first and only thing humanity has ever landed in the outer solar system. Everything else we've set down softly on another world has been closer to home, on the Moon, on Mars, on Venus, on a comet, or an asteroid. But out past the asteroid belt, out in the cold country of the giant planets, only one human-made object has ever come to rest on solid ground. And it came to rest on Titan. Cassini and Huygens reached Saturn in the year 2004 after a journey of 7 years through the dark, slinging past planets to pick up speed, falling all that long way out toward the rings. And the orbiter would go on working until 2017, 13 full years of looking and listening before it finally ran low on fuel and was deliberately steered into Saturn itself to burn up gently rather than risk crashing into one of the moons it had grown to love. But that's the end of the story, and we're at the beginning, because early on the 14th of January 2005, the little Huygens probe let go. It detached from Cassini and began to fall toward Titan. And I want you to imagine that fall, slow and strange, because it's one of the most peaceful descents in the history of exploration. First, the probe hits the very top of the atmosphere, going extremely fast, and a heat shield glows in front of it, taking the brunt of the entry. Then, as it slows, a parachute blossoms above it. And now Huygens is no longer falling so much as drifting, swinging gently beneath its parachute, sinking down and down through that thick orange haze for more than 2 hours. 2.5 hours of slow descent, sinking through layer after layer of organic smog, the world below slowly resolving out of the murk. And the whole time, it's looking, it's sniffing the air, measuring the chemistry, listening, taking pictures. It even recorded the sound of its own descent, a soft, low drumming as the wind moved past it, a sound from the sky of another moon. And then, at last, after that long, quiet fall, it touched down. Not on a sea as it happens, but near the equator, on dry land. And it found something that stopped scientists cold, in the best possible way. It found a landscape that looked, for all the world, like a dried-up riverbed back home. There were channels, branching, winding channels cut into the surface, exactly the shape that flowing liquid carves into a hillside, the shape of streams and rivers and the dry washes you'd find in a desert after the flood has gone. And scattered across the ground there were pebbles, rounded pebbles, smooth, water-worn cobbles, the kind you'd pick up at the edge of a stream and turn over in your hand, the kind that only get smooth and round when liquid has tumbled them against each other for a long, long time. Except these weren't stones, they were chunks of water ice, frozen hard as rock, but rounded and smoothed the way river rocks are smoothed by liquid, by methane, flowing across the land, rolling those ice cobbles over and over until their edges wore away. And the surface itself, where Huygens settled, was damp. Not bone dry, but damp, with a consistency the scientists described as something like wet sand or soft clay, a mud-like crust over a firmer base, as if liquid had been there recently, as if it was seeping up from below even then. A damp, muddy, river-carved landscape, complete with smooth pebbles on a world 1 billion kilometers from the sun. That's what we found on the 14th of January 2005, the only time we've ever set anything down out there. I love that little probe. It fell silently for 2.5 hours. It landed once. It sent home what it saw, and then its batteries faded and it went quiet forever. But in its few hours of life, it showed us that Titan reigns. That Titan has rivers. That this was not some frozen, dead, unchanging rock, but a living landscape in the geological sense, a place where weather happens, where liquid falls from the sky and carves the land and pools and dries and falls again. And now let me lift you back up off the surface for a moment, back up into the air, because Titan's atmosphere is its own quiet wonder, and it's the next piece of why this little moon is so strangely familiar. You and I live at the bottom of an ocean of air. Our atmosphere is mostly nitrogen, that calm, unreactive gas that makes up about 4/5 of every breath you take. Most of the air filling your lungs right now, in fact, is nitrogen, just along for the ride with the oxygen. And here is something that I think very few people know. Titan is the only other place in the entire solar system with a thick atmosphere of mostly nitrogen, just like ours. Out of every world we know, every planet and moon, only 2 of them are wrapped in a deep, nitrogen-rich air: Earth and Titan. About 95% of Titan's atmosphere is nitrogen, that same patient gas that surrounds you tonight. And it's not a thin wisp of an atmosphere either, it's thick, heavier than ours in fact. If you stood on Titan's surface, the air would press down on you with about 1.5 times the pressure you feel at sea level here on Earth, about 1.45 times to be exact. That's roughly what you'd feel a few meters underwater in a swimming pool, a gentle, even squeeze. So Titan isn't some airless ball of rock with a sky like the moon's, harsh and black and empty. Titan has a real sky, a deep sky, dense and golden, pressing down a little harder than the sky you know, but that sky is not blue, it's orange, a deep, smoggy orange all the way down. And the reason is one more strange and wonderful thing, and the last piece I'll give you before we drift off toward the seas themselves. High up in Titan's atmosphere, sunlight, what little of it reaches all that way out, has been quietly cooking the air for billions of years. It breaks apart the methane and the nitrogen and lets the pieces recombine into bigger, more complicated molecules, long chains of carbon and hydrogen and nitrogen, sticky, tarry, complex molecules that scientists call tholins. That's just the name for this orange, organic gunk, this smog of complex carbon compounds that forms up high and slowly drifts down. Tholins. And they're what give Titan its color. A permanent haze of organic smog hanging in the air, raining slowly down onto the surface over the ages, painting the whole world that warm, hazy, candlelit orange. And I want to pause on the word organic for just a moment, because it's a word that gets people excited, and I want to be gentle and honest about it. Organic, to a chemist, doesn't mean alive. It just means built around carbon, the element that life on Earth happens to be built from too. So when we say Titan's air is full of organic molecules of these tholins drifting down like a slow orange snow, we are not saying Titan is full of life. We're saying it's full of the kinds of carbon-based building blocks that here on Earth, life is also made of. It's a chemistry kit, a vast planet-wide chemistry kit, running quietly in the cold for billions of years, making more and more complicated molecules out of methane and nitrogen and the faint touch of sunlight. What those molecules add up to, whether they ever take any step towards something living, that's one of the great open questions, and we'll circle it gently before the night is through. But sit with the picture as it stands, a world with a thick nitrogen sky, like ours, with a higher air pressure than ours, a gentle, constant squeeze, with an orange haze of complex organic chemistry raining slowly down, with rivers and rounded pebbles and damp, muddy ground, with seas, real seas you can sail your radar straight through to the bottom of, and all of it built not from water but from fuel, frozen so cold that the water itself has become the stone. That, to me, is the heart of why Titan is so haunting. It is, in so many ways, the most Earth-like surface in the whole solar system. It is the one other place with rain and rivers and standing seas and shorelines and seasons and a thick, familiar sky. If you blurred your eyes at a photograph of a Titan coastline, you might mistake it for some dark beach back home, some moody shore at dusk, and yet every single piece of it is made from utterly alien stuff. The rain is gasoline, the rocks are ice, the sea is fuel, the sky is smog. It's Earth reflected in a strange and chilling mirror. Familiar shapes, impossible ingredients, a place that knows all of Earth's gestures, the falling rain, the carving river, the lapping shore, but speaks them in a chemistry we could never survive a single breath of. And here is what I really want you to carry into sleep tonight, the promise of where we're going as you drift off. Because Titan is not just a pretty, frozen postcard, a thing that happened once and then stopped. It is doing things right now, tonight, on a clock we can actually watch. There are mysteries on Titan that aren't ancient riddles carved in stone, but live, unfolding puzzles, things we caught in the act, things that broke our predictions while the spacecraft was watching. There are, for instance, islands that aren't there, islands that flash into view on the radar in one pass and are simply gone by the next. Here, then not here. We've nicknamed them the Magic Islands, and nobody is entirely sure what they are, or whether they were ever truly islands at all. We'll sit with that puzzle slowly a little later tonight. And there's something even stranger, something I find genuinely staggering. All that methane filling Titan sky, all that fuel that rains down and fills the seas, it shouldn't be there. Sunlight should have destroyed it long ago. The very same process that makes the orange haze is steadily tearing the methane apart, molecule by molecule, and by the math, all of Titan's methane should have been used up tens of millions of years ago, which on the scale of a 4.5 billion-year-old solar system is the blink of an eye. The methane should be gone, and yet there it is. The sky is full of it, the seas are full of it, which can only mean one thing. Something somewhere beneath the surface is refilling it. Something underground is resupplying an entire planet's atmosphere, topping it up faster than the sunlight can destroy it. And we do not know what that something is. Take a breath and feel the size of that. An entire world's air draining away on a cosmic clock and being silently refilled from below by a hand we cannot see. We'll come to that puzzle too, slowly, gently, and I'll be honest with you the whole way about what we know and what we simply don't. And because we don't know, because these mysteries are real and stubborn and still unsolved, we're doing something rather extraordinary about them. We're sending a drone, not a rover, trundling along on wheels, a drone with rotors that will fly. A nuclear-powered flying machine about the size of a small car called Dragonfly, which will lift off into Titan's thick, golden air and hop from place to place across the surface, sampling the ground directly, asking the moon itself the questions we can't answer from afar. It's the first time we'll ever have flown an aircraft on another world, and it will get there in the next decade. We'll talk about Dragonfly properly near the end, as our gentle reward for staying the journey. But there's no rush toward any of that. Not tonight. Tonight we have all the time in the world. We've only just arrived, you and I, standing on that dark shore under the orange dusk, watching the strange, clear sea lap so gently at our feet that it barely seems to move at all. We know now that it's fuel, not water. We know the ground is ice pretending to be stone. We know that little Huygens fell for 2.5 hours through the haze and landed among river-worn pebbles on damp, muddy ground, the only thing we've ever set down this far from home. And we know that the sky above us is thick and nitrogen-rich, and the warm orange of slow organic snow. So let's stay here a while longer on this shore and watch the weather, because the next thing I want to show you is how the rain actually works on Titan, how methane plays the part that water plays back home, how it rises into the sky as a vapor, gathers into clouds, falls as a slow, cold drizzle, runs in rivers, pools into those three great seas at the top of the world, and rises up again, the whole patient cycle turning and turning under a sun so distant it's barely more than a bright star. The only other place in the solar system where it actually rains, and rivers actually flow, and seas actually wait at the bottom of it all. But that's the next stretch of our journey. For now, just rest here on the shore with me. Let the clear, dark sea lie still in front of you. Let the orange light settle soft over everything. There's nothing you need to do, nowhere you need to be, no detail you need to hold. The methane will keep falling whether you follow it or not. The seas will stay clear and cold, and I'll keep talking slow and low while you sink a little deeper into the warm. Let me tell you, while you're settling, just how still these seas really are, because it's one more quiet puzzle, and it leads us gently upward. Cassini, watching for years, found those seas almost perfectly smooth. Mirror flat in places, the waves measured in mere millimeters, the surface so glassy you could practically have used it to fix your hair. And that's strange when you think about it, because the wind blows on Titan, and the liquid is thin and runny, far thinner than water, the kind of liquid that should ruffle into ripples at the faintest breath of air. And yet for years, the seas just lay there, calm as poured glass, barely a wrinkle on them. Where were the waves? Why was everything so still? We don't entirely know that one either. It may be that the winds were simply quiet during the long Titan season Cassini happened to be watching. It may be that the waves are coming slowly as the seasons turn and the northern summer winds begin to strengthen. Titan's seasons, you see, are enormous. Saturn takes nearly 30 years to circle the Sun, about 29 and a half, and Titan goes around with it, so a single Titan season, a single span of spring or summer or autumn or winter, lasts more than 7 Earth years. 7 years of slow summer, 7 years of slow winter. The weather there doesn't change in days or weeks, but over years and years, vast and unhurried, the clouds drifting, the rains shifting from one pole to the other, across a decade. A patient world where even the seasons are too big and too slow for a human lifetime to see more than a handful of. So perhaps the waves are simply waiting for their season. Perhaps as Titan's long northern summer comes on and the winds at last pick up, those mirror-flat seas will begin, ever so faintly, to stir. And perhaps that stirring is part of the answer to the magic islands, those features that flash on and off the radar. A faint ripple, a soft fizz, a low wave raised by a strengthening wind. But I'm getting ahead of myself, and we have all night, and you're getting sleepy, and that's exactly as it should be. Rest here a moment more on the shore of the clearest sea in the solar system, under the orange light, with the still dark liquid stretching off to a horizon you can only just make out through the haze. Hold the picture loosely, a sea of clear fuel, ground of solid ice, a sky of nitrogen and slow orange snow, river pebbles smoothed by methane, and somewhere beneath it all, in the dark, something quietly refilling the air of a world. We'll follow the rain next. We'll trace how the methane rises and falls and runs and pools. We'll name the 3 great seas at the top of the world and find out how deep they go and learn about the strange basins they sit in. But there's no hurry at all. Let your eyes stay closed. Let the shore hold you. The weather of Titan is turning slowly, slowly over its 7-year seasons, and we have nowhere else to be tonight but right here on its edge, watching it breathe. And so let's follow the rain. Somewhere high in Titan's orange atmosphere, far above the surface and above the thick blanket of Tholin haze, the methane rises. It evaporates off the surface of the seas in the long, slow warmth of a Titan summer, drifting upward as vapor, molecule by molecule, until it reaches the cold upper air, where it condenses again into cloud. The cycle is exactly what you know from home. Water rises from the ocean, forms cloud, falls as rain. But here, everything that plays the role of water is methane. Think of methane for a moment as a liquid that simply decided to do all the things water does on Earth, but at a temperature so far below freezing that water itself is nothing more than rock. At -179 degrees Celsius, water doesn't flow. It doesn't trickle. It doesn't pool in a basin or where a pebble's smooth. It simply sits there, hard and cold and permanent, the way granite sits in a valley at home. The bedrock of Titan is not silicate or limestone or basalt. It is water ice. The ground underfoot, if you could stand on Titan, would be ice as unyielding as any stone you have ever walked across. And onto that ice-stone bedrock, the methane falls. It falls as rain, not constantly and not everywhere. Titan is not a world of perpetual downpour. But when the clouds build in the right season and at the right latitude, the methane comes down in heavy, lazy drops, likely much larger than Earth raindrops because the gravity is so low. About 1/7 of Earth's pull, low enough that a falling raindrop doesn't accelerate to the speeds we know before it reaches the ground. It drifts. Titan rain is slow, and when it lands, it doesn't evaporate quickly either because the air above the surface, that thick nitrogen haze, is nearly saturated with methane vapor. The rain stays, it soaks into the porous organic sediment, it trickles into channels, and slowly over the long Titan years, it works its way toward the poles. The Huygens probe, when it descended on January 14th, 2005, was not coming down over the North Pole where the Great Seas cluster. It was descending near the equator in a region that looked, in the images that came back, like a dried-up lake bed. A flat plain with dark streaks. And on the slightly raised terrain nearby, Huygens photographed river channels cut into the landscape. Real channels, branching dendritic networks, exactly the shape you get when liquid runs downhill and carves its path into yielding ground. Methane-carved channels in a water-ice landscape. Below the channels, down at what would have been the drainage outlet, Huygens found rounded objects, smooth oval shapes, some of them centimeters across. Scientists called them pebbles, though pebble is a word that carries a lot of connotation. It makes you think of a stream bed, of a brook at the bottom of a garden, of something familiar and gentle. And that is not an accident because that is exactly what those shapes mean. They are water ice cobbles smoothed by liquid flow, tumbled and rounded over time by methane running over them and carrying them and rolling them against each other until their edges were gone. Pebbles made of ice, smoothed not by water but by a liquid that on Earth we burn as fuel. The surface where Huygens touched down was soft. The probe settled and reported a consistency like wet sand or firm clay over a harder base below, as if the top layer was damp, saturated with methane that had either rained recently or was seeping up from somewhere in the ground. A world that had been raining or was still, very slowly, doing so. All of this, the channels, the pebbles, the damp surface, was at the equator. But the Great Seas are not at the equator. The Great Seas are at the North Pole, and the methane rains are, at this point in Titan's long orbital cycle, concentrated in the north. The rain follows the seasons, and the seasons on Titan are vast. Titan orbits Saturn, and Saturn takes about 29.5 Earth years to complete one orbit around the Sun. That means Titan's year is also 29.5 Earth years long. And a year of 4 seasons divided by 4 gives you each season lasting roughly 7.5 Earth years. 7.5 years of northern spring, 7.5 years of northern summer, 7.5 years of autumn, and 7.5 years of winter. By the time a Titan summer is over, a child born at its beginning has started secondary school. By the time a full Titan year has passed, that same child has had time to grow up, have children of their own, and watch those children grow into teenagers. Cassini arrived at Saturn in 2004 during Titan's northern winter, and it watched for 13 years as the seasons turned. Not a complete Titan year, but enough to observe the change clearly, the slow migration of clouds from one pole toward the other, the brightening of the north as spring arrived, the building of cloud systems over the northern seas, the observation of actual rainfall, real storms caught in the act of dropping methane onto the surface. Cassini watched regions of Titan's surface darken after apparent rain events, the same way a sandy path on Earth darkens when the first drops fall, the surface becoming visibly wetter. Not metaphorically wetter, actually measurably darker in the way wet ground is darker than dry ground because the same physics applies whether the liquid is water or methane. This is the cycle in full. Methane evaporates off the northern seas. It rises and forms cloud in the cold upper air, carried by the winds of a slowly rotating world under a slowly tilting sun. It rains. The rain flows downhill into channels, down river networks carved into the icy bedrock over millions of years, and eventually toward the pole, where it pools again into the great seas and lakes. And then it evaporates again. The same molecule of methane that lands in Ligeia Mare today may have been rain over an equatorial plain 1,000 years ago. The same cycle, just unimaginably slow and cold and built from fuel. Now let's go north. Let's find the seas. They sit clustered around the North Pole in a way that has no precise counterpart on Earth. The South Pole has far fewer lakes, and the difference in itself is part of what Cassini documented. A world where the liquid is not distributed evenly, but is concentrated in one hemisphere, likely because the long northern winter keeps temperatures just low enough to preserve and accumulate the methane that drains there. 3 of the seas are large enough to be called seas: Kraken Mare, Ligeia Mare, Punga Mare. Punga Mare is the smallest of the 3 and in some ways the least studied. It sits at the very top of the world closest to the pole, and Cassini's radar didn't map it as thoroughly as the other 2. But it is there, another body of liquid hydrocarbon sitting quietly under the orange sky, as real as any lake on Earth. Ligeia Mare is the one we already visited, the clear one, the transparent one, the one that Cassini's radar passed straight through and found the floor of 160 meters below. 160 meters of near-pure methane-ethane liquid, so clean and free of dissolved solids and suspended particles that the radar signal went all the way down and came back with a clear echo from the bottom. Scientists who study Earth's oceans can only dream of water that clear. The most pristine mountain lakes on Earth are clouded by comparison. Ligeia Mare is a sea of almost supernatural transparency, sitting in the cold and the dark at the edge of Titan's north polar cap, and its floor is icy bedrock mapped by a spacecraft orbiting overhead. And then there is Kraken Mare. Kraken Mare is the largest sea on Titan. It is comparable in area to the Caspian Sea, the largest enclosed body of water on Earth, the one that sits between Russia and Iran, that has no outlet to any ocean. The Caspian Sea is roughly 370,000 square kilometers. Kraken Mare is in that class. It is a sea, properly speaking, not a lake, not a pond, a sea. And it is deep. In some parts, Cassini's radar did what it did so beautifully in Ligeia Mare. It saw the bottom. But in other parts in the central regions, the deepest heart of Kraken Mare, the radar signal went down and did not come back clearly. The bottom was beyond the reach of the measurement. What we can say is that Kraken Mare is at least 300 meters deep in places and possibly deeper. 300 meters is more than twice the depth of the North Sea between Britain and Scandinavia. It is a substantial depth of liquid hydrocarbon sitting at minus 179 degrees Celsius at the north pole of a moon so far from the sun that the sun from Titan's surface is just a very bright star in an orange sky. The floor of the central Kraken Mare is still, in a sense, a mystery. We know the liquid above it. We can model its composition, methane and ethane in a mix, with some dissolved nitrogen, perhaps traces of other organics. But the bottom, the actual seafloor of the largest sea on Titan, remains unseen. It is something for Dragonfly or some future mission to reach toward. What lies between and around these seas is also worth resting on for a moment. The lakes of Titan, the smaller bodies scattered around the North Polar region, often separate from the main seas, have a strange feature that scientists noticed when they looked carefully at their shapes. The basins they sit in are not rounded and gradual, the way you get when a river valley floods or a glacier scoops out a hollow. They are steep-sided, almost sharp-edged. The walls of the lake basins on Titan drop sharply down to the liquid surface below. And that kind of shape, on Earth, is what you get from dissolution. On Earth, there are landscapes called karst. You find them in places like the Yucatan Peninsula, or parts of Slovenia, or the hills of southern China. Karst forms when slightly acidic water gradually dissolves the rock it sits on, usually limestone, eating away at the stone from beneath and within until the ground simply collapses, leaving sinkholes and pits and steep-walled hollows. The lakes in karst country are often deep and circular and sharp-edged like holes punched in the ground rather than scooped out of it. The lakes of Titan's North Polar region look like karst. Scientists think the liquid hydrocarbons, the methane, the ethane, may be dissolving Titan's bedrock. Not limestone this time, but the icy and organic material that forms the ground. Just as water on Earth is very slightly acidic and eats slowly at limestone over millions of years, the liquid methane on Titan may be doing something analogous to the ice and organic compounds of its own bedrock, carving steep-walled basins by chemical dissolution rather than simple erosion. So the lakes may not just be sitting on the ground, they may have eaten their way into it. Slowly, over unimaginable spans of time, a liquid dissolving the floor it rests on. Whether that is exactly right is still an active area of study. But the shapes of the basins are real, and karst is the best analogy we have for how those shapes form. And it adds another layer to the picture of Titan. Not just a world where it rains methane, but a world where the rain and the lakes are slowly, patiently reshaping the very bedrock beneath them. Now move a little south, away from the polar seas down toward the middle latitudes and eventually toward the equator. The landscape changes, the lakes thin out and vanish, the ground becomes dominated by something completely different. Dunes. Not sand dunes in any familiar sense, because the grains of Titan's dunes are not made of silica. They are not quartz. They are dark and organic, and they are made of tholins, the same kind of complex hydrocarbon and nitrile particles that form in Titan's upper atmosphere under ultraviolet light and gradually snow down onto the surface over millions of years. Tholins, the word coined by Carl Sagan, just means muddy in Greek, a name for something deeply complex and not yet fully characterized, a whole category of organic molecules that form in the cold chemistry of an atmosphere rich in nitrogen and methane. These tholin particles drift down through Titan's atmosphere, like a slow organic snowfall, and accumulate on the surface near the equator, where the winds that flow in Titan's thick atmosphere push them into dunes. The dunes of Titan are enormous. They run for hundreds of kilometers in length, roughly parallel, oriented by the prevailing winds. They are hundreds of meters tall. They stretch across vast swaths of the equatorial region in patterns clear enough to map from orbit. From above, they look like nothing so much as a desert, a vast, dark, organic desert. The kind of landscape you might expect on a world that has had billions of years of organic chemistry raining slowly down from the sky. What is strange about the dunes is what they are made of. On Earth, a dune is made of rock ground down small by millions of years of wind and water. Titan's dunes are made of molecules that fell from the sky. Chemistry from the atmosphere, the products of methane and nitrogen reacting under UV light, settling down through the haze over geological ages and piling up into dunes that a human explorer, if one could somehow stand there in the dim orange light, would find strange in color and perhaps in texture, but utterly recognizable in shape. Great ridges of dark material, wind-shaped, stretching off to every horizon. They are the largest known reservoir of organic material on Titan's surface. Everything that's in those dunes started in the atmosphere. The methane that rises from the seas and the lakes is not just cycled back as rain. Some of it is destroyed in the upper atmosphere by sunlight, and its fragments are reassembled by the chemistry of that cold, dark, nitrogen-rich air into new, more complex molecules that drift down and pile up in those dark ridges near the equator. The dunes are, in a sense, the graveyard of the methane, the end point of one part of the cycle. And that word, graveyard, brings us to a question that has been waiting at the edge of this picture since we first began. Because if the upper atmosphere is continuously destroying methane, breaking it apart with ultraviolet light, turning it into ethane that rains out and into tholins that pile into dunes, then the methane in Titan's atmosphere is being used up. It is a resource being consumed. And if it is being consumed, it must have a source. We'll follow that thread carefully in a little while because it goes deep and it goes strange, and it is one of the most genuinely open questions in planetary science right now. But first, rest here a moment in the dune field, in the low orange light, with the great ridges of dark organic material around you in every direction, a landscape built from chemistry, a desert made of what was once air. Titan is doing something that no other world in the solar system does in quite this way. It is running a weather cycle, a full closed loop, like Earth, but built from different ingredients. The water cycle on Earth is so fundamental to the planet that we barely notice it as a cycle at all. We notice rain, we notice rivers, we notice the sea. We don't usually think of them as a single machine, turning continuously, every raindrop eventually finding its way back to cloud and back to rain again. But that machine is what makes Earth's surface dynamic, what carves the canyons and fills the basins and smooths the stones, what keeps the ground alive and changing. Take away the water cycle, and Earth would be a different world entirely. Titan has a methane cycle. It is doing the same thing. Evaporation, cloud formation, rainfall, river channels, lakes, seas, evaporation again. A machine running on a different fuel, at a different temperature, on a world with different gravity and a different sky, but following the same basic logic. The liquid falls from the sky, it runs along the surface, it pools, it rises again. It is a second example in the entire known universe of a world running a full surface liquid cycle. And until Cassini showed us what Titan looked like, we had only one example: us. That is not a small thing. It is worth pausing on, even in the quiet of wherever you are right now, with your eyes perhaps already drifting closed. We are not the only kind of world that does this. We knew theoretically that other liquids could form cycles on other worlds given the right conditions. But knowing it theoretically and seeing it, seeing the river channels, the rounded pebbles, the damp surface, the clouds forming and dissipating in real time, the seas at the North Pole with their transparent depths, seeing it is something else. Cassini gave us that. The seasons matter here too, and it is worth sitting with the scale of them for a moment longer. A Titan season is roughly 7.5 Earth years. During Cassini's entire mission, 13 years at Saturn, Titan moved from northern winter through northern spring and into the beginning of northern summer. Cassini watched the cloud patterns shift northward. It watched the large convective storm systems build over the North Polar region. It watched the dark, wet patches appear on the surface after rain events. And it could not watch a full cycle because a full Titan year takes 29.5 Earth years, and Cassini was only there for 13. But the piece it saw was enough to confirm that the cycle is real and active. The seasons do shift the rainfall, the lakes and the clouds do migrate with the sun. The atmosphere is not static, but is a dynamic, driven system, the same way Earth's atmosphere is driven by the seasonal tilt and the changing angle of sunlight. Titan tilts as Saturn tilts, and as Saturn slowly traces its long orbit around the Sun, the North Pole of Titan swings toward the Sun for several years and then away again, and the rainfall patterns and the cloud patterns follow. What does this look like from the surface? We don't know exactly because Huygens only touched down for a brief time in one place and told us what that one place was like at one moment, but we can imagine it from the data. Long dry years when the surface at the equator is dusty and the dunes sit undisturbed under a hazy sky. Then a heavy storm season when the rain comes down in bursts, flash floods pouring down the channels carved into the icy bedrock, the dry lake basins briefly glinting with collected methane, the ground darkening and shining and then slowly drying again as the season passes. And far to the north, a different rhythm, the slow, patient filling and evaporation of seas so large that their levels shift not year by year, but over decades, the clouds above them building and thinning as the long summer comes and goes. The southern polar region has its own lakes, fewer than the north and smaller, and those, too, shift with the seasons in ways Cassini was able to observe. Some southern lakes apparently shrinking or vanishing as the south moved away from the sun and into a long cold winter while the north brightened. The liquid moves with the warmth very slowly over timescales that dwarf human experience, but that are short enough for a long-lived spacecraft to detect. And throughout all of this, winding through the weather and the seasons and the lakes and the dunes, is the atmosphere itself. That thick, heavy, orange-hazed envelope of gas that keeps the pressure on Titan's surface at about 1.5 times Earth's sea level pressure. You would feel it if you could stand there. A slight heaviness to the air, a thickness not uncomfortable but noticeable. And every breath you tried to take would be almost entirely nitrogen. 95% of what surrounds you if you somehow stood on Titan is nitrogen, the same gas that makes up 78% of Earth's air. Titan and Earth, alone in the solar system, have dense nitrogen atmospheres. The similarity there is real, and it is one of the things that has always made planetary scientists look at Titan with a particular kind of attention. Two worlds with thick nitrogen skies, with active surface liquid cycles, with river channels and dunes and weather systems. One built from water and silicate rock, running at a comfortable 20 degrees Celsius in the sun. One built from methane and water ice, running at minus 179 degrees Celsius in the dim light of a distant star. The same architecture, different materials. Nature's way of showing you that certain patterns are not particular to Earth, but a rise from deeper physics that doesn't care what molecules you're working with. Above the surface, that nitrogen atmosphere extends much higher than you might expect for a moon of Titan's size. The low gravity means the atmosphere puffs outward, reaching up for hundreds of kilometers before it thins to nothing. And up in the highest layers, the atmosphere does something interesting. It spins. Faster than Titan itself rotates. The winds at high altitude in Titan's stratosphere complete a circuit around the Moon faster than the Moon's own rotation, a phenomenon called superrotation, and it is the same phenomenon you see in the atmosphere of Venus. Two very different worlds, and yet both of them showing you that a thick atmosphere, given the right conditions, doesn't always want to simply co-rotate with the ground beneath it. It develops its own momentum, its own rhythm, circling faster and faster as energy builds up in the high-altitude winds. This super-rotating atmosphere is part of how Titan's weather works at a large scale, how the heat from the distant sun is distributed around the Moon, how the circulation patterns are shaped, how the cloud systems form and travel. It is also, in a smaller way, part of what makes the dune fields look the way they do, since the dunes are oriented by the winds at the surface, which are themselves driven by the large-scale atmospheric circulation above. Everything connects. The chemistry falls from the sky and builds the dunes. The rain carves the channels and fills the seas. The seas evaporate and build the clouds. The atmosphere circulates and drives the winds and the seasons. The seasons shift the rain from pole to pole across decades, and running through all of it, the fuel of the whole machine, the methane. And here is where the picture starts to develop a shadow, a quiet, important shadow that you might not notice if you're only looking at the beauty of the cycle, at the rain and the rivers and the transparent sea. A question that sits underneath everything we've described and which has no clean answer. Where is the methane coming from? Not where does it go, we can see where it goes. It evaporates, it forms cloud, it rains, it runs in rivers, it pools in seas, it rises again. Some of it is destroyed in the upper atmosphere by ultraviolet light from the sun, broken apart into fragments that recombine into ethane and tholins. Ethane rains out and mixes into the seas. Tholins drift down and pile into dunes. The methane is consumed slowly but continuously, and the products of its consumption are accumulating in the seas, in the dune fields, in the organic chemistry of the surface. And solar ultraviolet light, at the rate it has been working since Titan first settled into its current state, should have consumed all the methane in Titan's atmosphere in somewhere between 10 and 30 million years. That is the number, 10 to 30 million years. A geologically short time, the solar system is 4.5 billion years old, which means 10 to 30 million years is less than 1% of the time Titan has existed. Titan should have run out of atmospheric methane long, long ago. And yet the methane is there, still there, abundant, filling the atmosphere, raining down, filling the seas. Something is replenishing it. Something underground or inside the Moon is doing something we cannot currently see or confirm, and it is the thing that is keeping the entire weather machine of Titan running. The rain, the rivers, the lakes, the seas, the dunes, the whole remarkable system we've been tracing. All of it is powered by methane, and all of it would shut down without a continuous supply, and nobody, right now, knows with certainty where that supply is coming from. That is not a small mystery. It is perhaps the deepest open question about Titan, and it sits quietly underneath all the beauty of the cycle, like a question you notice only when you stop and ask it. Where does the fuel come from? We'll follow that question soon because it goes down into the interior of the Moon, into the dark below the ice, into possibilities that range from the geological to the extraordinary. But not yet. The methane cycle is still turning, the dunes are still sitting dark and quiet near the equator. Under the haze, the three seas are still spread across the North Pole, Kraken Mare still going down beyond the reach of any radar we've sent. The picture is complete enough to hold in mind now. The full machine, running, turning, beautiful, and built on an unresolved question. Let your thoughts settle on that image for a moment, if they haven't already drifted somewhere quieter. The orange sky low above the dark surface of Ligeia Mare. The nearly invisible shoreline where the transparent liquid meets the ice rock beach. Somewhere to the south, a river channel carved into the frozen ground by rainfall that fell 1 million years ago and a rainfall that fell last season, indistinguishable. Somewhere east of that, a dune field stretching off to every horizon, made of chemistry that once was air. And high above, the thick nitrogen atmosphere rotating just a little faster than the moon beneath it, carrying clouds of methane vapor from the warming seas northward, where they will eventually cool and fall again. The machine breathes. Slowly, on a scale we can only just perceive, it breathes. And somewhere deep below the ice, below the methane seas, below the frozen water rock bedrock, deeper than any river channel or lake basin or karst dissolution could reach, something is or has been or may still be quietly adding to the methane in the air. We'll go there next, we'll go down. But first, there is a mystery that sits at the surface, not underground, not in the hidden ocean beneath the ice, not in the chemistry of cryovolcanic vents we haven't seen, right there on the sea itself. On the liquid, you could, in a thought experiment, reach down and touch with your hand. Between 2013 and 2016, Cassini made repeated passes over Ligeia Mare and Kraken Mare, sweeping its radar across the North Polar Seas, building up that detailed, patient portrait of a world with liquid on its surface. And during those passes, something strange happened, something that doesn't have a clean answer even now. Features appeared. Not features that had always been there, not permanent land masses, not stable islands the radar had simply missed on earlier passes. These appeared in a scan where they hadn't been in the scan before. Bright patches on the radar return sitting in the middle of the sea or along its shallower margins where the passes before had shown only liquid. Open sea. Nothing. And then they were there. And then, in a later pass, they were gone again. The team nicknamed them Magic Islands, which is honestly the right name because something in the language of science occasionally lands perfectly on what a thing actually feels like, and magic islands. Islands that materialize and then dematerialize, that are present one week and absent the next, is as accurate a description as a careful, evidence-driven field could produce. Take a moment with that. You're looking at a radar map of an alien sea on a moon more than 1 billion kilometers away, and there is something there that wasn't there before. Not an artifact of the sensor. The team checked for that repeatedly, because the obvious first response to a reading like that is to assume you're looking at noise or a calibration issue or a glitch in the transmission. But the features were real returns, strong enough to rule out simple instrument error. They were bright on the radar in ways that meant something physical was producing them. Something was there that scattered the radar signal differently from the surrounding liquid. And they were gone in the next pass. Between 2013 and 2016, Cassini documented multiple instances of these transient features in Ligeia Mare and in Kraken Mare, the two largest seas. They didn't always appear in the same place. They weren't always the same shape or the same size. Some persisted across more than one pass before vanishing. Others were there once and then not there again. The pattern, if you can call it a pattern, was inconsistency. They came and went on their own schedule, without apparent regard for where Cassini happened to be looking. So, what were they? There are 3 serious candidate explanations, and they are all still on the table. None has been confirmed. None has been ruled out. The honest answer to what are the magic islands is that we don't know, but we have some very good ideas, and at least one of them is particularly vivid. The first explanation, and currently the one that explains the most dramatic appearances most convincingly, is nitrogen bubble outbursts, fizzing seas. Titan's methane and ethane seas are not pure hydrocarbons. They also contain dissolved nitrogen. Nitrogen is a gas at normal pressures and temperatures, but under the conditions at Titan's surface, it dissolves into the liquid in meaningful quantities, much the way carbon dioxide dissolves into water to make a carbonated drink. The seas are, in a sense, lightly fizzy, holding nitrogen in solution, keeping it dissolved under the cold and pressure of the North Polar environment. Now think about what happens to a carbonated drink when conditions change, when you warm it up, when you relieve the pressure suddenly by opening the bottle. The dissolved gas comes out of solution. It forms bubbles, sometimes quickly, sometimes explosively. You've seen it 100 times. The foam rising fast up the side of a glass, the hiss from the cap, the champagne that loses half itself in the first few seconds because the pressure changed and the dissolved gas had somewhere to go. Titan's seasons are long. Saturn takes about 29.5 Earth years to complete one orbit of the Sun, which means each of Titan's seasons, spring, summer, autumn, winter, runs for a little over 7 Earth years. When Cassini was observing the North Polar Seas between 2013 and 2016, northern Titan was approaching summer. The sun angle was changing. The temperature of the northern seas was rising, very slowly, very slightly, but rising. And a small change in temperature or a small change in the pressure regime at the sea surface is enough to tip a supersaturated liquid, a liquid holding more dissolved gas than it strictly can at the new conditions, into releasing that gas. Suddenly, nitrogen comes out of solution. Bubbles form, not just a few, but potentially enormous numbers, frothing up through the liquid, rising to the surface in churning columns, bursting and releasing the nitrogen into the air above the sea. A fizzing event, a sudden outgassing, just like the opening of that carbonated bottle, but happening spontaneously in response to the slow, seasonal warming of an alien sea, and a sea surface covered in nitrogen bubbles in the middle of actively outgassing that looks very different on radar than a calm, flat, liquid surface. The bubbles roughen the surface. They create a texture that scatters the radar signal in a completely different way from smooth liquid. They could look, on a radar map, like something solid was there, like an island had materialized in the middle of the sea. Then the outgassing slows, the bubbles dissipate, the sea surface smooths out again. The radar sees nothing but liquid. The island vanishes. This is the explanation that most convincingly handles the most dramatic of the Magic Island appearances, and it has a satisfying physical logic to it. Titan's seas behaving like a bottle of carbonated water placed too close to the heater. It connects the Magic Islands directly to the seasonal cycle, which means they should be predictable in a broad sense. As northern summer deepens, the warming of the seas should trigger more and larger outgassing events. The Magic Islands, on this model, are a symptom of Titan breathing out. But the bubble hypothesis doesn't cleanly explain all the appearances. Some of the Magic Islands were smaller, less dramatic, less suited to a sudden outburst model. Which brings us to the second candidate, waves. This one requires a small setup because one of the most quietly striking facts about Titan's seas is how still they are. Cassini spent years scanning those North Polar seas, and for a long time, most of the mission, found them to be, in terms of surface texture, almost perfectly flat. The wave heights, when detectable at all, were estimated to be perhaps a few millimeters to a few centimeters. Tiny. For reference, a calm day on an Earth lake will still produce waves larger than that. A gentle breeze on an open sea raises ripples far more substantial. Titan's methane seas, for most of what Cassini observed, appeared to have nearly no surface texture at all. This is puzzling in its own right because Titan does have winds. The atmosphere moves, clouds travel, weather happens, and winds over a liquid surface should raise waves. The physics of wave generation is well understood. Wind stress on a liquid creates ripples, and ripples grow into waves given enough fetch, enough time, enough wind. Yet for years, Cassini's radar returned from those seas with essentially no wave signature. The leading explanation for the missing waves involves the timing. The northern seas were in winter and early spring during much of Cassini's observation window, when Titan's winds near the surface are thought to be gentler. The prediction is that as northern summer approaches, the winds will pick up and waves will follow. There is some evidence toward the end of the Cassini mission of increasing surface roughness on the seas, hints that the seasonal shift was slowly beginning. But in that context, even very small waves, capillary waves, the tiny ripples produced by the lightest possible surface breeze, could produce a detectable radar signature. A patch of the sea surface that happens to be roughened by a transient gust, even slightly, even producing waves of only a few centimeters, could return the radar differently from the surrounding glassy liquid. It could look like something was there. A brief roughening, a transient wind-raised surface texture lasting for the duration of one Cassini pass, and then smoothing back out. A magic island made of nothing but a ripple, smaller, less dramatic, shorter-lived than a major nitrogen outburst, but physically quite plausible. And it wouldn't require anything unusual. Just ordinary Titan weather, a gust of wind crossing the sea at the wrong moment, catching the radar at just the right angle. This explanation is harder to rule out for the subtler appearances, and it's entirely possible that not all magic islands have the same explanation. Some might be bubble outbursts, some might be faint waves. The sea doesn't need to be doing only one strange thing at a time. And then there is the third explanation, the one that arrived most recently, and adds a different kind of strangeness to the picture. In 2024, researchers led by a team at Cornell worked through the physics of what happens to methane ice at Titan's surface conditions. Not the liquid methane in the seas, but solid chunks of methane that has frozen into a porous, rigid structure. And they found something interesting. Porous frozen methane, under the right conditions, can float. The structure of the ice, its porosity, the way gas is trapped within it, gives it a density low enough to sit at the surface of the liquid sea. Not permanently, though. The liquid infiltrates the porous structure over time, saturating it, filling the trapped gas spaces with liquid, slowly making it heavier, and eventually heavy enough to sink. Chunks of porous frozen methane floating at the surface, then becoming saturated, then sinking. Frozen methane icebergs, in a sense, icebergs made of the same chemistry as the sea they float in, rising and sinking on a time scale of hours or days, visible on radar when they're at the surface, invisible when they sink. The Cornell-led modeling in 2024 showed that this mechanism is physically viable under Titan conditions. These floating then sinking solids could contribute to the magic island phenomenon, particularly for appearances that don't fit the clean fizzing outburst model and for features that seem to persist across more than one radar pass before disappearing. A chunk of frozen methane drifting in the sea, partially afloat, partially submerged, sinking slowly as it saturates, that could produce a radar return that fades gradually rather than cutting off sharply between passes. So you have three explanations. Each handles a slightly different subset of the observations. Each is physically grounded and modeled carefully, and none is confirmed. What is confirmed is that Cassini caught something real appearing and disappearing on those seas repeatedly across 3 years. The magic islands are not a rumor. They are not a misreading of the data. They are documented in the scientific literature, observed in multiple sea basins at multiple times, under conditions that have been checked and cross-checked. They are there. What they are is still genuinely open. There is something quietly wonderful about that. A world more than 1 billion kilometers away is doing something in its seas. Nitrogen burping through the liquid, or wind raising tiny waves on a calm surface, or chunks of frozen methane ice cycling up and down. And the honest answer from the people who know the most about it is that they're not certain which one it is, or whether it's all three at once. The magic islands sit in the literature as a real, documented, unsolved phenomenon, and the scientific community is waiting for more data to distinguish between explanations. The data, as it happens, is coming, and we'll get to that. But let's stay with the surface for just a moment longer, because there's one more thing to notice about those seas, the thing hiding inside the missing waves puzzle. The near flatness of Titan's seas, the mirror-like surface that Cassini found year after year, isn't just an interesting observation, it's a diagnostic. It tells you something about the liquid itself. Methane, as a liquid, has a very low viscosity, lower than water's. It flows easily, pours readily, spreads thin across a surface. Low viscosity liquids, in general, are the ones that respond most readily to wind. They're easy to disturb, easy to ripple. If anything, you'd expect methane seas to develop surface waves more easily than water seas, not less easily. And yet Cassini found the surfaces nearly flat for years. This tells researchers something important about the wind regime, that surface winds near the North Polar Seas were weaker than expected during the winter and early spring period of most of the Cassini observation window. It's also one of the reasons the bubble hypothesis is attractive. It explains surface texture appearing without requiring wind. If the flat seas are flat because the winds are genuinely calm and the magic islands appear in the absence of significant wave-driving wind, then something other than wind has to produce the radar texture. Bubbles rising through a calm surface do that without needing any breeze at all. The flat seas and the magic islands are connected, in other words. They're two aspects of the same slowly shifting situation on a world whose seasons run on a 7 Earth-year clock, whose North Polar region was just beginning to warm during the years Cassini had left to watch it. Now, there is one more thing about these northern seas, and it doesn't sit on the surface at all. It sits far, far below it, beneath Ligeia Mare and Kraken Mare, beneath the icy bedrock of the North Polar region, beneath the karst dissolved lake basins and the methane water table seeping through porous rock. Deeper than the deepest river channel, deeper than anything the Huygens probe touched, or any radar we've sent has reached. Down there, if the measurements are right, and the evidence for this is taken seriously by planetary scientists, there is another ocean. Not a methane ocean, not a hydrocarbon sea of any kind. This one is water, liquid water, almost certainly mixed with ammonia, which acts as a kind of antifreeze, keeping the water liquid at temperatures far below what pure water needs. A global subsurface ocean of liquid water hidden beneath Titan's ice shell, somewhere between tens and perhaps over 100 kilometers below the surface. The evidence comes from Cassini's gravity measurements and from careful analysis of how Titan's rotation wobbles slightly as Saturn's gravity pulls on it. A completely frozen interior doesn't respond to gravitational tugs the way a partially liquid one does. The tidal deformation of the body, the slight flexing as Saturn pulls, is measurably different. Cassini's data showed a body with a liquid layer inside, consistent with a global subsurface ocean. This kind of tidal response measurement has also been applied to other icy moons, Europa, Enceladus, Ganymede, and in each case it has pointed toward hidden liquid water. Titan is an ocean world, and not just in the way we usually mean. Titan is a double ocean world, i.e. with hydrocarbon seas on its surface and a water ocean hidden in its depths. This makes it, by some measures, the most complex ocean environment in the solar system after Earth. You have liquid on the surface, shaped by a full atmospheric cycle, evaporating and raining and flowing and standing in named seas. And then so far, below that you could stack several Mount Everests in the gap, you have another liquid body entirely, chemically alien to the surface seas, but potentially vast, potentially ancient, and potentially connected, very distantly, perhaps through cracks in the ice, to everything above it. The relationship between those two oceans, the surface methane seas and the subsurface water ocean, is not well understood. They don't mix in any direct way that we know of. The ice shell between them is thick and cold and solid, a barrier kilometers deep. But the ice shell is not necessarily inert. If there is heat flowing upward through it, from radioactive decay in Titan's rocky core, from tidal heating as Saturn's gravity kneads the interior, that heat could drive geological processes. It could weaken the ice in places, it could drive cryovolcanic vents upward through the shell, channels through which material from the subsurface ocean might very slowly reach the surface. And what would that material carry? That's the question that matters most, and it's the one that will take us in a moment from the surface of the seas to the atmosphere above them and to the deepest mystery Titan holds. But first, let's stay just a little longer with the idea of the hidden ocean, because it deserves to be felt before it's analyzed. Imagine yourself above Titan's North Pole, above Ligeia Mare, above that near-transparent sea of methane ethane so pure that radar saw straight to its bed 160 meters down. The orange sky above you, the dark liquid below, the mirror-flat surface with perhaps a ripple somewhere near the margin. And beneath that surface, the frozen water bedrock going down and down. And beneath even that, kilometers of cold, dark ice. Ice under pressure, ice that has never seen sunlight, ice that formed in the early solar system and has been accumulating in layers for billions of years. And somewhere beneath that ice in the dark, under enormous pressure, liquid water. Warm enough to stay liquid, barely. Mixed with ammonia so that its freezing point is pushed down further than water alone could manage. A global ocean, potentially as deep as an Earth ocean, covering the entire interior of the Moon below the ice. It has never been directly sampled. It has never been seen. We know it is probably there from the way Titan wobbles in Saturn's grip, from the mathematics of tidal flexing applied to the density profile of a moon we've measured from orbit. But it has never been touched. The surface methane seas, those at least we have images of. We have depth soundings, we have the Huygens probe that sat on the surface nearby and breathed Titan's air for over an hour. We have years of radar mapping by Cassini, the named features, the documented depths, the transparency of Ligeia Mare measured in real radar returns from its bed. The subsurface ocean is for now inference, a very well-grounded inference supported by data and consistent with the physical models of what icy moon interiors should look like, but inference nonetheless, and yet it matters enormously for understanding what Titan is doing and why, because the subsurface ocean is one of the candidate explanations for the most puzzling thing about the Moon's atmosphere. The thing that makes the methane question not just interesting but urgent. We'll get there now. Something has been running in the background of everything we've talked about in this part of the night's journey. While we've been watching the magic islands appear and disappear on the radar maps, while we've been thinking about waves that don't form on a nearly flat sea, while we've been following the idea of a hidden water ocean down through the ice, something has been happening in the atmosphere above all of it. Sunlight has been hitting Titan's upper atmosphere. Not much sunlight. Titan is more than 9 times farther from the Sun than Earth is, which means it receives only about 1% of the solar energy that falls on Earth's surface. The Sun from Titan's surface looks like a bright star, barely a disk dimmed further by the thick orange haze. But even 1% of the sun's output falling on a moon over billions of years is a great deal of energy. And ultraviolet light, the highest energy part of the solar spectrum, is doing something very specific in Titan's upper atmosphere. It is destroying methane. The process is called photolysis. Ultraviolet photons carry enough energy to break the bonds that hold a methane molecule together. The 4 hydrogen atoms wrapped around a single carbon, the simplest organic molecule, the first rung of organic chemistry. UV light hits the methane, breaks the bond and the molecule fragments. The pieces: hydrogen atoms, carbon atoms, molecular hydrogen, reactive hydrocarbon fragments, drift apart and recombine into other things. Ethane, acetylene, more complex hydrocarbons, tholins eventually, the orange organic solids that make Titan's haze, carbon atoms that will eventually rain down to the surface as organic particles, building the dune fields, coating the landscape in the dark chemistry of fragmented air. Methane goes in, other things come out. The methane is not recovered, it is converted. This happens continuously. Every day the sun rises over Titan's atmosphere and UV light chips away at the methane there. Not dramatically, not noticeably, on any human timescale. The rate is small, tiny even, compared to the total reservoir of methane in the atmosphere, in the seas, dissolved in the liquid, but it is relentless. It has been happening for the entire age of the solar system. And when you do the math on how much methane is in Titan's atmosphere and how fast UV light destroys it, the answer that falls out is stark and strange. At the current rate of photolysis, all of the methane in Titan's atmosphere should be destroyed in roughly 10 to 30 million years. 10 to 30 million years sounds like a long time. In ordinary human experience, it is incomprehensibly long, but in the context of the solar system's age, 4.5 billion years, it is a geological blink. It is less than 1% of the solar system's lifetime. It's a moment. The solar system did not form 10 to 30 million years ago. Titan did not form 10 to 30 million years ago. Titan has been orbiting Saturn for essentially the entire age of the solar system, and yet its atmosphere is full of methane. Right now, in quantities that suggest an active, ongoing reservoir, not a dwindling remnant. If methane were simply sitting there in the atmosphere from some original supply laid down when Titan formed, it would be gone by now. Gone by so long ago that there would be no trace. The chemistry would have moved on entirely, all the methane converted to ethane and tholins and acetylene, the reservoir depleted, the orange sky perhaps dimmed or shifted in color as the feedstock for haze production ran out. But the orange haze is there, the methane is there, the seas are there, methane, ethane liquid sitting under a methane-rich sky, evaporating and raining and cycling, just as we've been watching it do through the whole of this night's journey. Something is replacing the methane that the sun destroys. Something, somewhere, is adding methane to Titan's atmosphere at roughly the rate that UV light takes it away, or has done so in pulses throughout Titan's history. Some source hidden from direct observation, continuously or episodically feeding a planet's atmosphere from below, and we don't know what it is. This is the methane budget problem. Not a theory, not a hypothesis, a genuine observational constraint on Titan's interior and history. The math runs clearly and the conclusion is inescapable. There is a source. The question is where and what and how. The candidates, and there are several, each with its own evidence and its own difficulties, are what we'll spend the rest of this part of the night with. Because the methane budget problem is not a background curiosity, it is the central, unsolved question about Titan, the thing that connects the surface chemistry to the interior geology, to the deep history of the Moon. And it is precisely the question that the next decade of solar system exploration is being organized around answering. The first candidate is cryovolcanism, ice volcanoes. On a rocky world like Earth, volcanic activity drives hot, molten rock, magma, up through the crust, out through vents, onto the surface as lava. The driving force is heat from radioactive decay in the planet's interior and from residual heat left over from the planet's formation and from the energy released as the planet's iron core solidified. Rocky volcanoes erupt silicate minerals at temperatures of hundreds to over 1,000 degrees Celsius. On an icy world like Titan, the same physics can operate, but with completely different materials. The rock of Titan's crust is water ice, and the magma is not molten rock, but a slurry of liquid water, possibly mixed with ammonia, which lowers its freezing point, or liquid methane, or both, rising from a warmer reservoir below and pushing up through the ice toward the surface. The vent isn't pouring out basalt at 100-200 degrees. It might be oozing slushy water ammonia at temperatures still well below 0 Celsius, or exhaling methane gas from a pressurized underground reservoir. Cassini looked hard for evidence of cryovolcanism on Titan. It found some features that are suggestive. Rounded, dome-like terrain, a few regions where the surface looks reconstructed in ways that could be consistent with fluid flow from below. A feature called Sotra Patera was identified as a possible cryovolcanic caldera. But the evidence is ambiguous, nothing as clear as a smoking vent, nothing as definitive as fresh lava flows on a geologically young terrain was definitively confirmed. Titan's thick haze and the limits of radar mapping from orbit make it hard to get the detail needed to say with confidence, this is a cryovolcanic feature and not something else. But cryovolcanism is not just plausible as a source of methane. It's expected if Titan's interior is warm enough, and there are reasons to think it might be. Saturn's tidal pull on Titan generates heat through tidal friction as Titan's interior flexes. Radioactive elements in Titan's rocky core produce heat as they decay, just as they do in Earth's interior. That heat has to go somewhere. One possibility is that it drives convection in the subsurface water ocean, which drives slow geological overturn in the ice above, which occasionally produces cryovolcanic venting at the surface. If Titan's interior is warm enough, and the subsurface ocean strongly suggests it is, then ice volcanoes are a natural consequence, and they could carry methane up from depth. Not just gas, but methane that has been stored in the interior, perhaps since the moon formed, perhaps produced more recently, by chemical reactions in the warm rock-water interface at the ocean floor, where water and rock react in ways that can generate methane abiotically, that is, without biology. The second candidate for the methane source is closely related, and it starts with the subsurface ocean itself. If there is a global liquid water ammonia ocean beneath Titan's ice shell, then at the interface between that ocean and the rocky core below it, the seafloor of the hidden ocean, there is rock in contact with warm liquid water. This is exactly the setting in which hydrothermal chemistry operates on Earth, in Earth's deep oceans, where water percolates through hot rock and emerges at hydrothermal vents, carrying dissolved minerals, heat, and chemicals produced by the reactions between water and basalt at high temperature and pressure. One of the things that hydrothermal reactions can produce, given the right conditions of temperature, pressure, and rock composition, is methane. On Earth, this process, called serpentinization, when certain iron and magnesium-rich rocks react with water, is known to generate methane as a byproduct. Abiotic methane production in Earth's deep crust and mantle is real and documented. It may be happening at the floor of Titan's hidden ocean, generating methane that then works its way up through the ice shell, through the cryovolcanic system, to the surface and into the atmosphere. This is appealing because it connects two things we know exist: the subsurface ocean and the methane problem, in a straightforward way. If the ocean exists and if the rock beneath it is reactive with water under heat, then methane is a likely product. The unknowns are how much and how fast, and whether the plumbing exists to get it from the ocean floor to the surface atmosphere in sufficient quantities to match what the sun is destroying. The third candidate is methane clathrate. A clathrate is a structure in which molecules of one substance are trapped inside a lattice formed by molecules of another. In the case of methane clathrate, also called methane hydrate, molecules of methane are caged inside a crystalline structure of water ice. The cage holds the methane stable, locked in place, as long as the temperature and pressure conditions are right. But if conditions change, if the temperature rises or the pressure drops, the cage structure becomes unstable. The ice lattice collapses and the methane is suddenly released. On Earth, methane clathrates are found at the bottom of deep oceans and in permafrost, and their instability under warming conditions is one of the things that makes climate scientists nervous. A large-scale release of clathrate methane under rapid warming is a scenario with potentially significant atmospheric consequences. On Titan, methane clathrate could exist in enormous quantities in the ice shell itself, locked up at the temperatures and pressures found at various depths within the several kilometers thick ice crust. Stability of these structures depends sensitively on temperature. As Titan's interior generates heat, as tidal flexing warms the ice from below, as the slow geological evolution of the Moon shifts conditions at depth, clathrates could destabilize. Not all at once, not explosively on a human timescale, but steadily over geological time, releasing their stored methane into the rock and ice above, which eventually finds its way to the surface and into the air. The clathrate hypothesis is attractive because it offers a reservoir mechanism, a way to store methane from Titan's formation in the early solar system, locked safely in ice, and release it slowly over billions of years in a way that keeps the atmospheric supply going even as UV light chips away at it. It's a slow-release capsule buried in the Moon's own structure. The difficulty is that clathrate destabilization would need to be tuned, releasing methane at roughly the right rate to balance the photolysis loss, without being so fast that the reservoir depletes quickly or so slow that the atmosphere still starves. Getting the rate right from the physics of the interior is not simple, and there's no direct measurement of how much clathrate may be present or how stable it currently is. And then there is a fourth possibility, one that the scientists working on Titan are careful to flag as speculation, not evidence, not a detected signal, not a claim, but a hypothesis that the physical conditions on Titan do not rule out, and that the chemistry of the methane budget problem makes worth acknowledging honestly: life. Not the dramatic, technologically sophisticated life of science fiction, not beings standing on the shore of Ligeia Mare watching our probes approach, something far simpler, single-celled or simpler still organisms, if organisms is even the right word for what would be an entirely alien biochemistry, that could, in principle, operate in Titan's cold methane environment, using liquid methane as a solvent the way Earth life uses liquid water, and producing methane as a metabolic byproduct the way Earth's methanogenic archaea, microbes that live in swamps and wetlands and the guts of animals, produce methane as a waste product of their chemistry. Scientists have thought seriously enough about this to work out what a methane-based cell membrane might look like. On Earth, cell membranes are built from phospholipids, molecules with a water-loving head and a water-avoiding tail, which spontaneously arrange themselves into the bilayer structure of every cell membrane, because water is the universal solvent their chemistry operates in. In liquid methane, a different set of molecules, specifically nitrogen-containing compounds called azotosomes, could in principle form similar membrane-like structures that are stable in methane rather than in water. Azotosomes are a theoretical construct worked out by researchers at Cornell who ran the thermodynamic calculations to see if such structures were physically viable. They appear to be, on paper, in models, There is no azotosome in any sample from Titan. There is no detected biosignature. There is no observation that requires biology as an explanation where geology would not also serve. The methane budget problem is a genuine unsolved mystery, but it does not require life. The geological candidates alone are sufficient to explain it if any of them is operating at the right rate. What is true is that if life does exist on Titan, any kind of life, however strange, using Titan's chemistry, however distantly analogously to the way Earth life uses Earth's chemistry, it would be producing methane, and it would be very hard to tell the difference from orbit between methane produced by a cryovolcanic vent and methane produced by a community of methane-exhaling microbes in the cold dark below the surface. That is precisely why Dragonfly matters. But that's part 4. For now, let the candidates stand as they are: cryovolcanism, hydrothermal chemistry at the ocean floor, methane clathrate releasing from the ice, and the carefully flagged, evidence-free, but physically non-excluded possibility of methane cycling life in the hydrocarbon depths. 4 open doors, each plausible, none confirmed, none ruled out. And above all of them, the atmosphere keeps its methane, the seas keep cycling, the dunes sit dark and still near the equator, the magic islands flicker in and out of existence on the radar maps, and the sun keeps destroying methane at a rate that should have run the whole reservoir to zero long before your grandparents' were born. Something is filling it back up. Titan is answering a question we haven't fully asked yet. There's one more piece of the methane budget to hold alongside this, a piece that comes not from the missing methane but from what the missing methane leaves behind. When UV light destroys methane in Titan's upper atmosphere, one of the primary byproducts is ethane. The photolysis chain isn't random. It produces specific molecules in specific ratios, and ethane is one of the most abundant results. That ethane doesn't stay in the atmosphere forever. It rains out. Over billions of years, the photolysis of methane should have produced and rained out to the surface an enormous quantity of ethane, enough, in some models, to fill Titan's known seas several times over with a deep, thick layer of essentially pure ethane. Titan's seas do contain ethane. Cassini detected it there, but they contain a mixture, methane, ethane, and some dissolved nitrogen, not the overwhelming ethane ocean that the full photolysis history of the Moon would seem to predict. Where is all the ethane? It might be dissolved in the subsurface. It might be absorbed into the organic sediment. It might be sequestered in forms that Cassini couldn't easily detect from orbit. Or it might mean that the methane supply history is more episodic than continuous, that the atmosphere was not always as methane-rich as it is now, that there were periods when the methane ran lower, the ethane production slowed, and the inventory accumulated differently over geological time. The ethane budget and the methane budget are really 2 aspects of the same problem. They both point at the same hidden interior process, the same unknown source, the same geological or perhaps biological engine running somewhere beneath the surface of a world that shouldn't, by the math, still have this much methane in its sky. This is not a solved problem, it is an active one, being worked on now with the tools we have and being aimed at with the tools we are building. And the tool we are building is extraordinary. It's coming in the next part of tonight's journey. A machine unlike anything we have sent to another world, not a rover rolling cautiously across a flat plain, not an orbiter circling from a safe distance, but something that will astonishingly fly. That will lift off from the surface of Titan, rise into that thick nitrogen air, cross kilometers, and come down somewhere new, and ask a completely different set of rocks and sediments what they're made of, because that's what you do when a world is keeping secrets in its chemistry. You go there, you land, You reach out and touch the surface. You run the samples through the instruments and let the molecules speak for themselves. Dragonfly will do that. In the 2030s, if all goes well, a nuclear-powered drone the size of a car will fly across Titan's surface and ask the questions that orbiting radar and a 2005 landing 650 kilometers from the nearest sea could not answer. But the methane budget problem that remains, for now, open. The magic islands remain, for now, unresolved. The subsurface ocean remains, for now, inferred. Titan is holding its secrets with the patience of a world that has been doing whatever it is doing for 4.5 billion years and has no reason to hurry. Take a breath. Let the picture sit for a moment. The fizzing seas, the sinking methane ice, the deep hidden water, the sun slowly destroying an atmosphere that something keeps quietly refilling from below. The machine is still running, the questions are still open, and we are almost ready to go down to the surface and ask them directly. So let's go there. Let's follow the thread of the methane, because it leads somewhere strange and deep and genuinely unresolved. And it might be the most important question we're carrying into the 2030s. Here is the thing about Titan's atmosphere. You've heard by now that it's thick, that it presses down at 1.45 times Earth's surface pressure, that it's mostly nitrogen, that it's wrapped in that orange haze of tholins and hydrocarbons. And you've heard that methane plays the role here that water plays on Earth. The rain, the rivers, the lakes, the evaporation, the whole patient cycle of a weather system running on a different molecule. But here's what that means when you stop and think about it carefully. Methane doesn't just sit there. It doesn't stay methane forever, not in a place where sunlight reaches, even dim and distant sunlight filtered through all that haze. Ultraviolet light, UV, is a demolition crew. It breaks molecular bonds, and the bond holding together a molecule of methane, which is one carbon atom and 4 hydrogen atoms arranged in a neat little package, is not strong enough to survive indefinitely against the slow, patient hammering of ultraviolet radiation from the sun. This process has a name. It's called photolysis. Photo meaning light, lysis meaning to break apart. And it happens in Titan's upper atmosphere every day, every year, year after year, for billions of years. UV light streams in, strikes methane molecules, and pulls them apart, stripping away hydrogen atoms and leaving fragments that go on to build other things. Ethane, tholins, the whole zoo of complex organic molecules that give Titan its color and its chemistry, which is fine, which is in fact part of what makes Titan so interesting. Except for this, photolysis is irreversible. Once UV light destroys a methane molecule, that methane is gone. It becomes something else. It doesn't come back. And scientists have been able to calculate how fast this happens, how quickly ultraviolet light, at Titan's distance from the sun, destroys the methane in the atmosphere. And the answer they get is deeply unsettling. All of the methane in Titan's atmosphere should be gone in roughly 10 to 30 million years. Let that sit for a moment. 10 to 30 million years sounds like a long time. On a human scale, it is unimaginably vast. But on a planetary scale, on the scale of a solar system that formed 4.5 billion years ago, 10 to 30 million years is nothing. It is a rounding error. It is a single page in a very long book. And Titan has been there for 4.5 billion years. So either Titan ran out of methane a very, very long time ago and has been sitting there as a frozen, methane-free nitrogen world for the last several 100 million years, which would make it a fundamentally different object than the one Cassini found. Or something is refilling it. Something is, right now, adding methane to Titan's atmosphere fast enough to keep up with the destruction. Something underground or deep inside the moon, or hidden somewhere in the ice, is feeding that cycle, replacing what the sun removes, maintaining the weather, the rivers, the lakes, the seas, and we don't know what it is. That is the methane budget problem, and it is not a small puzzle at the edges of planetary science. It is a central question about what Titan actually is and what it has been doing for the last 4.5 billion years. Whether the methane we see is ancient, continuously replenished from a deep reservoir, or whether we happen to be watching at an unusual moment when some large, one-time release is still playing out. Neither answer is confirmed. Both have implications that reach far beyond Titan itself. So let's walk through the candidates, the serious ones, the mechanisms that scientists are actually investigating, the ones that have real physics behind them, because this is where the story gets genuinely strange. The first candidate is cryovolcanism. On Earth, volcanoes work because the interior of the planet is hot enough to melt rock, hot enough to push that melted rock up through cracks in the crust and out onto the surface. On Titan, the interior is cold compared to Earth's interior, but it's not cold by absolute standards. There's heat left over from formation, heat generated by the slow decay of radioactive elements deep inside the moon. And if that heat is sufficient, or if it's enough to maintain pockets of liquid or semi-liquid material beneath the ice, then there could be what planetary scientists call cryovolcanoes. Ice volcanoes, not rock, not lava, but ice and water and ammonia pushed up from below and vented out onto the surface or into the atmosphere. And if that material contains methane, if there are reservoirs of liquid methane, or methane dissolved in the subsurface fluids, or methane clathrates breaking down in the warmth near these vents, then cryovolcanism could be the answer. It could be the mechanism that replaces what photolysis destroys. Cassini looked for cryovolcanic features on Titan. It found some candidates: smooth regions, features that looked like they might be lava flows of ice and ammonia slush, but the evidence was never definitive. Cryovolcanism on Titan is plausible. It is consistent with the data. It is not confirmed. The second candidate is the subsurface ocean. You heard about this ocean earlier tonight. The global layer of liquid water mixed with ammonia, sitting beneath the ice shell, inferred from Cassini's measurements of how Titan flexes and rotates. That ocean is real as far as the data can tell us. And an ocean of liquid water is not a passive thing. It can hold dissolved gases. It can react with the ice and rock above and below it. And one of the things it could, in principle, do is hold vast quantities of methane in solution, or produce methane through chemical reactions. Water reacting with minerals, for instance, in a process that on Earth is called serpentinization, which can release hydrogen and enable the formation of methane through further reaction. If the subsurface ocean is producing methane, or if it's sitting on top of a rocky seafloor where those reactions are happening, then it could be slowly outgassing methane upward through the ice, feeding the atmosphere from below. Again, this is a candidate, not a confirmation. The ocean is inferred, its chemistry is unknown, and whether it produces methane in quantities sufficient to explain the atmospheric inventory is an open question. The third candidate is methane clathrate. A clathrate is a structure where one type of molecule forms a cage and traps another molecule inside it. Ice, water ice, can form these cages naturally, and methane is an excellent guest molecule. Methane clathrate, also called methane hydrate, is found on Earth in deep ocean sediments and in permafrost, where the right combination of pressure and temperature keeps the ice cage stable and the methane locked inside. Titan's interior could contain enormous amounts of methane clathrate, ice laced through with methane, stable at depth, held together by the pressure and cold of the interior. And if something disturbs those conditions, if a pocket warms slightly, if the pressure changes, if the ice structure shifts, the clathrate becomes unstable. The cages break. The methane escapes. This could be happening slowly and continuously, a steady seep of methane from destabilizing clathrate layers, or it could happen episodically, big releases when conditions change, followed by quiet periods. Either way, clathrate is a real reservoir of methane that could plausibly be feeding the atmosphere. And then there is the fourth candidate, which sits at the far edge of what scientists are willing to discuss seriously, and which I want to be very clear about because it's the kind of thing that can run away from itself if it's not handled carefully. The fourth candidate is chemistry that we haven't identified yet, or in the most speculative version, biology. Now, when scientists talk about the possibility of life on Titan, they are not talking about the kind of life we have on Earth. They are not talking about anything that uses liquid water as a solvent, because liquid water on Titan's surface is a solid. It's the bedrock. They are talking about something hypothetical, something theoretical, something that has never been observed and may not exist at all. A form of chemistry, possibly a form of life, that uses liquid methane as its solvent instead of water. Researchers have done the theoretical work to ask whether this is even possible. They have proposed what such organisms might look like at a molecular level, cell membranes that don't use the phospholipid bilayers that Earth life uses because those require oxygen and water to function, but instead something like what's been called an azotosome, a membrane built from nitrogen-containing organic molecules, which could in principle maintain its structure in liquid methane. They have proposed that such organisms, if they existed, might consume hydrogen gas dissolved in the methane seas, react it with acetylene on the surface, and release methane as a byproduct. And that kind of metabolism, methane releasing, hydrogen consuming, is exactly the kind of signature that would look from the outside like an extra, unexplained source of methane in the atmosphere. This is a hypothesis. It is a thought experiment run carefully by scientists asking, is this physically possible? The answer to that question appears to be, maybe we don't know enough to rule it out. That is very different from saying there is life on Titan, there is no evidence of life on Titan, there is no confirmed biosignature. There is only the theoretical possibility that the chemistry could, in principle, support something, and the acknowledgement that the methane budget problem is exactly the kind of anomaly that a metabolic process could, in principle, produce, which is why it is mentioned at all, not as a conclusion, as a direction to look. And this brings us finally to the ethane problem. Because photolysis of methane doesn't just destroy the methane, it produces byproducts. The main one is ethane. Every time UV light breaks apart a methane molecule, the fragments recombine in various ways, and one of the most abundant products of that recombination is ethane, a molecule with 2 carbon atoms and 6 hydrogen atoms, liquid ethane. The same ethane that's mixed into the seas. And here's the thing. If photolysis has been running for hundreds of millions of years, or billions of years, even if methane is being continuously replenished, the ethane should be accumulating. Every cycle of destruction and replacement adds more ethane to the inventory. The seas should be getting more ethane-rich over time. And when scientists look at the total inventory, as at how much ethane is actually in the seas and lakes compared to how much should have built up over geological time, the numbers don't quite close. The inventory of ethane in Titan's surface liquids is lower than the models predict it should be if photolysis has been running for as long as we think it has, which means either photolysis hasn't been running for as long as we think, suggesting the methane is a relatively recent addition which opens its own set of questions. Or there's somewhere the ethane is going that we haven't accounted for, trapped in the subsurface, locked into clathrates, sequestered somewhere in the organic sediment. The budget doesn't close, the inventory doesn't balance, and an inventory that doesn't balance means there's something in the accounting we're missing. All of these threads, the magic islands, the mirror flat seas, the subsurface ocean, the methane that should be gone and isn't, the ethane that should be there and partly isn't, they are not separate puzzles. They are different windows onto the same underlying question. What is Titan actually doing in its interior right now? What is the engine running this machine? And the only way to find out is to go there, to the surface, to sample the chemistry directly, to reach out and collect a piece of Titan and ask it, instrument by instrument, what it's made of and what it's been doing, which is exactly what Dragonfly is going to do. Let me tell you about Dragonfly because it is unlike anything we have sent anywhere before. It is a rotorcraft, a drone. 8 rotors arranged in 4 pairs, all designed to bite into Titan's thick nitrogen air and generate lift. And it is roughly the size of a car. A real car, not a toy, not a small prototype. A machine with real mass and real science instruments packed inside it. It will land on Titan, it will rest on the surface, it will power up its rotors, and it will fly. Not metaphorically, not in some abstract sense. It will actually rise from the surface of a moon of Saturn, fly through the air, cross several kilometers, and land somewhere new. And then it will do it again and again. Over a planned mission lasting several years, it will hop across Titan's surface, visiting multiple sites, collecting samples from each one, running them through onboard instruments, and building up a picture of Titan's surface chemistry in a way that no orbiter circling from hundreds of kilometers away and no single lander pinned to one spot could ever achieve. It's powered by an RTG, a radioisotope thermoelectric generator, the same technology that powered Cassini's instruments. It's a device that uses the heat produced by the natural radioactive decay of plutonium-238 to generate electricity. Not a nuclear reactor in the fission sense, no chain reaction, just the slow, steady, reliable heat of a radioactive isotope doing what radioactive isotopes do, and a thermocouple arrangement that turns temperature differences into electrical current. Why plutonium? Why not solar panels? Because Titan is, by any practical standard for solar power, dark. It orbits Saturn at roughly 9 to 10 times the Earth's distance from the Sun, which means sunlight there is already about 1% of what Earth receives. And then that already faint sunlight has to fight its way down through the thick haze of Titan's atmosphere, through the tholins, through the orange smog, through the opacity of a nitrogen sky that scatters and absorbs light at every altitude. By the time you reach the surface, there is not enough sunlight to run a mission of the complexity and power demands that Dragonfly needs. You would need solar panels the size of a small building to collect enough energy, and you still wouldn't be guaranteed enough on any given day. Plutonium-238 doesn't care about the haze. It generates heat from inside, from the physics of the atom itself, reliably, day and night, through every season, through every storm, regardless of where Titan is in its long year and how thick the clouds are overhead. It is the right power source for this mission. There is no alternative that works as well. Dragonfly is scheduled to launch in July 2028. That's the target. And if everything goes to plan, it will arrive at Titan in approximately 2034, in the mid-2030s, after a journey of roughly 6 years through the outer solar system. And where it's going to land first is particularly interesting. The target landing site is near the Selk impact crater. An impact crater on Titan is not simply a hole in the ground. When a large meteorite or comet fragment strikes Titan's surface with enough energy, it doesn't just excavate a bowl, it releases tremendous heat. And that heat matters enormously on a world like Titan, because Titan's subsurface contains water ice. The impact melts it. Briefly, perhaps for centuries, perhaps for a few thousand years, you have liquid water pooled in and around the impact crater. And liquid water mixed with the organic molecules on Titan's surface is a chemical environment that planetary scientists find very compelling, because the chemistry that produces the building blocks of life, amino acids, nucleotides, complex organic polymers, tends to run in environments where liquid water meets organic carbon compounds under some source of energy. That's the recipe that seems to work, as far as we know, from Earth's early history and from laboratory experiments simulating early Earth conditions. Selk Crater may be a place where billions of years ago, or merely millions of years ago, liquid water mixed with the rich organic chemistry of Titan's surface and ran for long enough for interesting things to happen. The impact melt solidified long since. Selk is not an active water lake today, but the chemistry that ran during that window may have left traces, frozen into the ice, locked into the sediment, preserved in the organic deposits around and within the crater. Dragonfly will land there and sample those deposits directly. Its instruments include a mass spectrometer, which can take a tiny sample of surface material, dust, sediment, a scrape of regolith, and vaporize it and sort its components by mass, identifying the molecules present with remarkable precision. It carries cameras to document the geology of each site. It carries a meteorology package to measure atmospheric conditions, temperature, pressure, wind, building up the first in situ weather record from Titan's surface since Huygens descended in 2005. It may carry a seismometer, listening for vibrations in the ground that could tell us something about Titan's interior structure. And because it can fly, because it can cover real distance and visit genuinely different terrain, it can sample not just one kind of surface chemistry, but multiple kinds. It can visit the dune fields with their dark organic tholin sand. It can visit the crater. It can travel to the edge of a lake basin and sample the materials there. It builds a comparative picture. It asks, does the chemistry here match the chemistry there? Where does the organic complexity go up? Where do the molecular building blocks concentrate? Those are the questions that answer the bigger question. Is Titan a world that has, or has had, or could, in principle support, some form of chemistry complex enough to be called prebiotic? And prebiotic means not life. It means the chemistry that could come before life, the chemistry that on Earth eventually produced life, whether or not it has done so on Titan. Dragonfly is not a life detection mission in the strict sense. It's not carrying a test for biological signatures in the way that some Mars missions have been designed, but it's sampling the surface chemistry of a world that has all the ingredients that on Earth eventually led to biology. Organic molecules in abundance, a history of liquid water in impact craters, a current supply of chemical energy in the form of the disequilibrium between hydrogen and acetylene and methane. It's asking, what is the chemistry doing? How complex has it gotten? Where on the ladder from simple organic molecules to something genuinely interesting does Titan sit? And when you think about Dragonfly against the background of everything we've discussed tonight, the magic islands, the methane that refills itself, the ethane inventory that doesn't close, the subsurface water ocean we can infer but not see, the mission starts to feel like more than a clever engineering achievement. It feels like a necessary act of inquiry, like there is a question Titan has been sitting on patiently for 4.5 billion years, and we are finally building the instrument capable of going down to the surface and asking it out loud. Flight on Titan, by the way, is not the heroic engineering challenge it would be almost anywhere else. This is one of the things about Titan that is almost poetic, if you think about it. The dense air, the low gravity, about 1/7 of Earth's, similar to the Moon. Put those two things together and the atmosphere is so thick relative to the pull of gravity that generating lift is almost easy. A rotorcraft that would struggle to fly in Earth's thin air at high altitude, or that would be completely impossible on the Moon where there is no air at all, works beautifully on Titan. Scientists have noted that if you were standing on Titan's surface in a suit that could keep you warm, ignore, for a moment, the impossibility of surviving at minus 179 degrees Celsius without extraordinary technology, and if you attached fairly modest fabric wings to your arms and flapped, you could probably generate enough lift to fly. The physics genuinely permits it. The air is that thick and the gravity is that low. Titan is a world where human-powered flight would be plausible by physics alone, even though no human will be going there anytime soon. Dragonfly exploits this completely. Its 8 rotors are designed for Earth's air, roughly, but when you run those same rotors through Titan's nitrogen at 1.45 Earth atmospheres, with a gravity barely stronger than the Moon's, you get lift with room to spare. The vehicle can carry scientific instruments and batteries and structure and still rise off the ground and fly for tens of minutes at a time, covering kilometers, landing precisely where the science team aims it. That kind of mobility is revolutionary for planetary exploration. Every rover we've sent to the Moon, to Mars, has been ground-bound. It rolls, it gets stuck in sand, it navigates around rocks, it climbs carefully up slopes. The area it can survey in a mission is limited by what wheels can cross. Dragonfly leaps all of that. It doesn't need roads, it doesn't need flat terrain. It can fly over a dune field and land in the middle of the next one, or approach a crater from above and set down inside it. In a single mission, it will cover more ground than any Mars rover has in its entire operational life, and it will do it on a world where the ground itself is made of things we have never handled. Organic sediments, water ice bedrock, tholins compressed into dunes, crater, ejecta mixed with surface chemistry, lake margin deposits where the methane sea has lapped at the shore and left whatever it carries dissolved in solution. We have not touched any of that. Huygens touched one spot, a damp, muddy, rock-strewn surface near the equator, 650 kilometers from the nearest standing body of liquid. It gave us 22 extraordinary minutes before Cassini moved out of radio range and the signal was lost. 22 minutes on the surface of Titan. That is the entirety of humanity's tactile experience of that world. Dragonfly gives us years, and so for now, we wait. We carry the unanswered questions with us. The magic islands that appeared between 2013 and 2016 in the radar passes and vanished between them, whether bubbles or waves or methane ice that floats and sinks, are still appearing and vanishing on a schedule we can't yet predict. The methane is still being destroyed by UV light and still being replaced by something underground. Cryovolcanism, or the deep water ocean outgassing, or clathrate destabilizing, or something else we haven't named yet. The seas are still mirror flat beyond what the models say they should be, waiting for the northern summer winds to tell us whether that changes. The ethane is still accumulating somewhere we can't account for. The subsurface ocean is still there, deep and cold and mixed with ammonia, inferred from the way Titan flexes but never directly seen. Titan is not waiting for us. It doesn't know we're coming. It has been doing whatever it does for 4.5 billion years without our attention, and it will keep doing it regardless of whether Dragonfly arrives on schedule or not. The methane cycle doesn't pause, the seas don't drain, the photolysis doesn't stop. Whatever is refilling the atmosphere keeps refilling it steadily on its own geological clock. But we will be there. In the 2030s, if all goes well, a nuclear drone will descend through that orange nitrogen sky, through the tholin haze, past the altitude where the photolysis is happening, down through the cold air that smells if you could smell it and survive the temperature and the lack of oxygen, of gasoline and almost nothing else, down to the surface where the dunes rise hundreds of meters and the sea is only kilometers away and the chemistry of the universe is doing something patient and complex and not yet understood. It will touch down on Selk Crater. It will take a sample. It will run the molecules through the mass spectrometer and send the data back across 1.2 billion kilometers to a team of people in a room somewhere on Earth who have been waiting years for exactly this information. And we will read what the surface says. Maybe it says, here are simple organics, no more complex than what you'd expect from ultraviolet chemistry, and nothing else. That would be an answer. A complete, satisfying answer that tells us Titan's chemistry hasn't gone further than the physics of sunlight striking molecules in the air. Maybe it says, here are amino acids, here are the nucleotide components. Here is chemistry more complex than UV alone could produce, chemistry that requires something else, some additional energy source, some additional ingredient, some concentration mechanism, some reaction pathway we haven't accounted for. Maybe it says something we don't know how to interpret yet because we're asking questions framed by Earth, and Titan is answering in a language we're still learning. Any of those answers would be extraordinary. Any of them would change how we think about this moon and about the question it has been quietly posing to planetary science since Cassini first turned its radar toward those dark polar seas and saw something it wasn't entirely ready for. Take a moment, if you're still with me, to let the scale of this settle. You are lying somewhere in the dark, or sitting, or curled up on a couch with a lamp still on. And somewhere out there, right now, past Mars, past the asteroid belt, past Jupiter and its storms, a ringed giant called Saturn is moving slowly along its 30-year orbit, and circling that planet is a moon the size of Mercury, wrapped in an orange haze, with seas of liquid methane pooled near its north pole. And those seas are doing things we can't explain, and the sky above them is being slowly emptied of its methane by a sun so distant it looks like a bright star and no warmer than a streetlight at 100 meters. And in the depths of that moon, something is replenishing what the sun removes. Quietly, steadily. We don't know what, but something has been doing this for millions of years, maybe longer. Something is running a machine that keeps Titan's cycle alive. And here is the part that I find most remarkable. Not just that Titan exists, but that we found it. That in the entire scope of human history, in the very brief moment we have been capable of building instruments sensitive enough to see across the solar system, Cassini arrived at Saturn in 2004 and spent 13 years watching a moon that by any right we should not yet be able to understand. And in those 13 years it found the magic islands. It measured the depths of seas made of fuel. It watched the seasons turn and the clouds shift and the rainfall darken the surface. It found evidence of a global ocean hidden under the ice. It did all of this from orbit, from hundreds of kilometers away, with radar and infrared and radio waves, without ever touching a surface that would tell us directly what it's actually made of. And we are about to touch it. You are part of the species that built Cassini, that built Huygens, and dropped it through an alien atmosphere with a parachute in January of 2005 and listened to it drum against the surface. That is building Dragonfly right now, assembling a nuclear-powered drone that will fly across a moon of Saturn in the 2030s and tell us what the surface chemistry is actually doing. And wherever you are tonight, in whatever corner of the world, whatever hour it is in your particular piece of dark, that is yours. That inquiry, that reach, that refusal to accept it's complicated as a final answer. It belongs to you as much as to anyone in a laboratory or a mission control room. The universe has been running its chemistry for 13 billion years without us. Methane cycling through alien atmospheres, seas of hydrocarbons pooling at the poles of frozen moons, UV light tearing molecules apart, and something deep underground, putting them back over and over on a clock measured in millions of years. All of that was happening long before anyone was here to wonder about it, long before anyone built a radar instrument sensitive enough to catch an island appearing in a sea of methane and then disappearing again. And it will keep happening long after tonight. But right now, in this particular sliver of time, we are watching. We noticed the islands, we spotted the paradox in the methane budget. We measured the depth of a sea we can't swim in and found it transparent as glass. We inferred an ocean of liquid water we've never seen, from the way a moon 1.2 billion kilometers away flexes slightly under the gravitational tug of its planet. We are, in the fullest sense, paying attention. And Dragonfly will be our hand outstretched, our fingers finally brushing the surface of a world that has been doing something extraordinary for longer than our planet has had complex life. I hope, wherever you are tonight, that something in this journey gave you the particular kind of quiet that comes from thinking about big things. Not the anxiety of vastness, not the feeling of being small and overwhelmed, but the other feeling. The one that comes when the universe turns out to be stranger and richer and more specific than you expected. When the answer to what's out there turns out to be seas made of fuel, islands that appear and vanish, an atmosphere that should have been gone 100 million years ago, and a machine that flies. That feeling is real. It's yours to keep. I asked at the start of tonight, wherever you are in the world, what time is it in your corner of the dark? I'm curious. Tell me in the comments, and tell me if there's a particular mystery that the magic islands, the methane that keeps coming back, the nuclear drone descending through that orange sky, that you find yourself turning over as you drift. I'd love to know where these questions land. If this slow journey through Titan's strange and beautiful chemistry gave you something tonight, a like and a subscribe really do help. Small creators like me rely on your support to keep these nights going. And to those of you who are already here, already subscribed, already part of these quiet orbits, thank you. Genuinely, it means more than I can easily say. Titan is out there right now. The methane is cycling. The seas are flat and cold and full of secrets. And somewhere in a clean room on Earth, Dragonfly is being built. Good night from up here in orbit. I'll keep watch while you drift.